Hello, everybody. This is Deepak Vij from Future Way Cloud Lab. I, along with my colleague Phu Tran, will cover details for Mizar network virtualization layer for our next generation Centaurus cloud platform. So just kind of a very high level description of what Mizar is. Mizar is a programmable data plane for multi-tenant network services at scale. To set the background, why do we need another cloud networking solution? Why do we need that? So we built we'll kind of go through that. We'll set the background. We built Centaurus cloud platform to meet the needs of very large enterprises, which may typically include Fortune 100 companies who deploy their infrastructure at very massive scale. Okay. So the large scale cloud platforms such as Centaurus, they need to be able to scale up in order to support enterprises' entire global footprint, you see. So in order for us to be able to accommodate all that, we set a design target such as, we may have a scenario where you have 100,000 virtual machine endpoints per network, and in combination with many of these networks. Okay, so you can see the scale. The environment, the cloud environment is very dynamic. So you have all these the lightweight containers and serverless functions come and go. In a fraction of a second, you may have thousands of these endpoints that they need to be provisioned and managed, basically. So it's not a typical old static environment where you maybe spin up VMs few times, maybe 100 times a day max. So as opposed to that, we have a very dynamic environment. So we wanted to support rapid provisioning of cloud resources very quickly and efficiently. So we set a performance goal in order to achieve high throughput, low latency, and consistent network performance in a multi-tenant environment. So that's the key thing. Multi-tenancy, VPC, is built from ground up and is a first-class citizen as part of our platform. So now from a scalability perspective, so just going back to VPC, this is similar to what public cloud providers provide as well. VPC multi-tenant environment in AWS, Google, Microsoft. And from a scalability goals perspective, our networking solution should be capable of provisioning VMs or container endpoints concurrently, thousands per minute, and be capable of routing and managing communication among millions of network endpoints, and be capable of elastic scaling of network services, be able to create an extensible cloud network of pluggable network functions. We'll get into a lot of details about that. We have kind of very interesting kind of discussion on that. And then last but not the least, the unified network of various workload types. So one common interface, network interface for various type of workload, such as container, VM, doesn't matter what the workload is, you get the same networking interface when you provision or manage an endpoint. So that's that was just the kind of a background. Now, with that as a background and requirements, we came to the conclusion that the flow programming, current flow programming, typically employed by OVS, like solution, networking solution, may not be the right model in order for us to be able to scale up to this, there's such a large environment. Okay, so we'll get into a lot of details, what that means. Now, so what are the problems? Why do we think that the flow rules are not going to be able to meet such an environment? Okay, so one of the key thing is just to kind of set the background, in a typical network solution such as OVS, a control plane programs flow tables on each of the virtual switches on each host using the open flow protocol. Okay, And then suppose a customer wants to add a new virtual endpoint into a specific network. So, and then let's assume that network has 100 endpoints spread across multiple hosts. Okay. So now what control plane, when you're adding a new endpoint, what control plane will do is it will program flows on all the other hosts that have the VMs in this particular network where this endpoint is being added, so that those VMs can reach the newly added endpoint, VM in this case, you see. So you have to go and program, add a flow rule table on all the virtual switches on all those hosts, okay? And additionally, the control plane also program flows on the virtual switch for the VM where this host and a new endpoint is being added, so that the new VM can reach rest of the network, you see. So you can see the problem actually. It's about the number of flows per host and the number of hosts must be programmed, when you adding new endpoints, you see. So the total programming overhead becomes really very massive. It becomes product of the number of endpoints in a host multiplied by the number of hosts in the overall system, basically. So this results in you can see the it's very obvious, such an architecture does not meet the scaling goal. The provisioning of rapid provisioning of such a massive scale, and then at the runtime packet processing, because you have so many flow rules to deal with, it becomes the CPU memory utilization becomes a big bottleneck actually, you see. So that's what we meant, that the current flow rule programming model doesn't measure up to the such a large scale environment. So to address these scaling problems, challenges, we built, we call Mizar network solution cloud networking in order to route traffic for virtual networks and be able to provision endpoints in such an environment. Okay. Now, there are state of the art, there's a lot of work going on actually. So currently OVN, the control plane folks are doing a pretty good job of kind of optimizing the moving away from old Neutron control plane towards the new OVN controller, which is based on the optimized databases versus the RabbitMQ model, which they employed as part of the Neutron control network. So they've done a great job actually. So adding a single port reduced from tens of seconds close to 1 second. So this is really great actually. So this is a good achievement, but this is still not enough, you see, especially that it still doesn't scale up to the scale, the environment which we are talking about. And the reason being the fact that the underlying problem is the fact that it's still based on top of OVS, and which typically uses flow rules to be able to manage the overall networking environment. Actually, that's the OVS flow rule programming model is the main challenge. So there's been a lot of work done. Google, Andromeda, these folks, they're trying to minimize the flow rules in their system. So what they do is they send all their packets to a thing called hoverboard actually, and then they monitor periodically all the flows in the system in hoverboard, and then find specific flows to be offloaded using direct path, fast path with flow rules. So on a periodic basis, they selectively offload some of the flows out of a hoverboard and use direct path, with their hardware optimizations in order for and two endpoints to talk to each other, basically. So you can see that all of these efforts, OVN, Andromeda, it pretty much boils down to a single idea, is that to find ways to reduce the number of flow rules passed down to the data path, okay? So we stopped for a second. So we said, we asked ourselves a question. So what does it take for us to build a next generation overlay network that doesn't use any flows at all? Okay. So what if we program the data plane just like you would build a regular distributed system application. So do away with all of these flow rules altogether, and build the data plane as a regular distributed system application. So we took that tag or approach and went with that model, distributed system application model, basically. Okay. And then there's no need in such an environment. We're working in a this is a very specialized use case, cloud networking. Everything is very deterministic. So there's no need for MAC learning or flooding flooding the tunnel, those kind of age-old networking designs. So that's what we kind of there's no need for such design old networking designs. Okay, so now XDP. So just want to briefly touch upon what XDP is, because this is what we use. So instead of using the flow rules, we built the entire networking cloud networking layer using XDP. And but before we get into that, I just want to kind of a high level describe what XDP Express Data Path. So in 2018, a group of kernel engineers published a paper about the XDP. Okay, but this has been going on for a while. I think this came out around 2016, and the goal is to run custom eBPF programs within the device driver of the NIC. Okay. So these eBPF programs are really small programs, 4K in instruction size, written in generic language such as C, but you can actually write them in Rust as well. Okay, and these programs are verifiable programs. So that when the kernel loads them, without worrying about causing any possibility for a crash. So it verifies, kernel upfront verifies that there's no loop, there's no wrong pointers or memory allocation, et cetera, et cetera. So it's all these programs are verifiable. And once the program is loaded as part of the kernel, so when the packet comes in from the NIC, you can actually run pretty much very high level logic in a typical data structures such as array, hash tables, and then make an appropriate action to the packets. And those actions are typically either pass them to the networking subsystem within the kernel, or transmit them back to the NIC, or even redirect them to another interface or drop it. Okay. So that's kind of a pretty high level description of what XDP is. Okay. And so that's what we ended up doing actually. So as I mentioned, so we built our entire networking solution based on XDP protocol. So what we did was, so we take an approach and say that, okay, so we remove everything. We got rid of Open vSwitch, Linux bridges, IP tables, and we replace them with XDP program on the main interface, and we call it a transit XDP, basically. Okay, and then we have another XDP program on the VF pair that connects to a container or a VM, and we call it a transit agent XDP. Okay, and these two programs share eBPF maps, which are programmable from the user space by the transit daemon. You can see that here, transit daemon, transit XDP, and then you have a transit agent XDP. And you may have multiple networking interfaces on a host. So for each one of those interfaces, we have a corresponding transit XDP program, and that corresponds to a droplet. So for each interface, my network interface, you'll have a droplet basically. So that's the kind of overall architecture. So when the management plane from a management plane perspective, if we would like to push the configuration, you just make a RPC call to the user space program, and these user space program, the transit daemon, will populate your regular maps, hash tables inside the kernel, basically. Okay, and in a cloud when you're building network functions, functions, the functionality you typically have can be pretty much reduced to 3 or 4 constructs. And they are typically, you either encapsulate or decapsulate a packet, or you modify the outer packet header and forward it, modify the inner packet header and forward it, or drop the unwanted packet. These are the typical the constructs you employ when you building services such as NAT or your load balancing, and so we are able to perform all of this, and we are able to build the network services using the 4K XTP program, basically. So that's kind of a high level architecture what we have. Okay. Now, drilling down more into it, so if you drill down more into it, from a packet architecture standpoint, we have these transit XTP programs running on RxQ of the NIC of the main interface, okay, on every host, okay, and we have a transit agent running on the RxQ of the VF pair. So whenever packet comes in, and the ingress packet comes in, we can redirect it to the TX queue, bypassing the entire kernel in the root namespace to the container, okay? And for the egress packet, we take the packet from the container and redirect it to the TX path on the main interface. And then again, we bypass the root namespace. So that's kind of a high level architecture we have for Mizar, okay? Now, so you can see that. So what we have done is, what we have done so far is that we have actually, we look at the network interfaces on all the hosts in the data center, and we treat them as programmable tiny servers, basically. You see, so you have all these tiny servers running on the every network interface of every host in the data center. So we can load programs there. We can have regular data structure, and then we have a mapping table that so that has a mapping. So we have an endpoint. Where is it hosted, that endpoint? So you have that mapping in that on those hosts, all the hosts in the data center, and then we put all these exact same programs over all the hosts in the data center. So that's what our basically the overarching architecture is. Okay. Now, so what we do is, on a management plane perspective, we assign label to one of the hosts and we call it a bouncer. Okay. Bouncer is just an abstract object in the management plane, basically. Okay. So now, when we creating a new endpoint, okay. So as you know, as I mentioned that initially, that when you're creating a new endpoint, you have to go across all of the hosts and update the flow rules on the virtual switches of every host for that network. As opposed to that, when you're creating a endpoint, a container, for example, we do 2 RPC calls. The first RPC call goes to the host in which we are going to provision the container, and basically tell the XTP program that your bouncer is on host B. Okay, so you can see that here, that we're adding this new endpoint 10.0.0.0.1, and we tell that endpoint, your bouncer is on host B. That's the only thing we do. And then we have another RPC call that tells RPC call to the bouncer host that we call the bouncer host that 10.0.0.1 is hosted at host A. Okay, So we just need these two RPC calls to provision the container, and that's it. That's pretty much it. Okay. Now, so let's say now we add another container. We add another endpoint, and we do exactly the same thing. So we telling the bouncer on host B that we have another endpoint in 10.0.0.2, which is hosted at host C. Okay, and that's it, and we're all done basically. And on host C, we tell the endpoint 10.0.0.2, your bouncer is on host B, basically. Okay, so these RPCs are standard RPC calls, gRPC calls, basically. They typically take, for example, 20 millisecond for RPC call to the bouncer to update the bouncer, and then maybe more or less about 300 milliseconds or so to provision the container endpoint. Okay. Now, from a packet processing perspective, so what happens is, so when the endpoint on host A wants to communicate with endpoint on host B, the first step is that the XTP program takes the packet and encapsulates into a GNI packet and then transmits the packet out to the bouncer, because that program doesn't really know anything about the network. Okay, it doesn't know where the host, the endpoint 10.0.0.2 is, except that you have a packet, send it blindly to the bouncer. So it sent it to the bouncer B. Okay. Now, so this is where the packet goes to bouncer B. So so host B is where we actually have the mapping. Okay, that says that 10.0.0.1 is the host A and 10.0.0.2 is on host C. So we rewrite the outer packet. So on the bouncer, when the packet comes to bouncer, the packet rewrites the outer packet to host C and sends the packet out to host C. And then we're done, basically. So packet originated from host A, went to bouncer, and from bouncer, send it out to host C. Okay. However, you can see that there's a problem there, you see. So by doing all this, we've added an additional extra hop in between. So every packet that goes from source endpoint to the destination endpoint, you have to go through a bouncer to do that, you see. So that's problematic. So when you're dealing with the line rate performance of packet processing, this is a major problem. Okay, so we decided, okay, so how are we going to solve this problem? So what we did was we added modified our protocol so that we actually bypass, in order for us to bypass this hop. Okay, so we changed the XTP program and added an ARP request, basically. See, and changing the XTP is pretty straightforward, actually. Dynamically, we just write the C code, loading actually on the fly without any packet interruption at all. You see. And also modified a little bit the transit agent XTP program behavior, in which we have to add a little bit of more information into a Geneva option. Okay, we'll get into that detail, actually. Okay. So now what happens is, so our request comes from host A, okay, and comes from the endpoint 10.0.0.1, and then it says any queries for host 10.0.0.2. Where is 10.0.0.2? It goes to the bouncer, the ARP request. But the bouncer has the ARP responder capability built in. So what it actually does is it replies back to the host A, says that I know where 10.0.0.2 is, and he modifies the Geneva option saying that 10.0.0.2 is actually on host C. Okay. So when the packet is received back at host A, it adds this to the local endpoint map. So that's saying that 10.0.0.2 is at host C. Okay. So so now when the first packet so now the ARP processing is over. So host A knows how to reach 10.0.0.2 because he knows that that endpoint is in host C. Okay. So when the first packet comes from host A, the flow, the coming out from 10.0.0.1, we added just one single bit in the Genie packet and say that this is the direct message. Okay. So now when the packet is received on host C, it knows that it actually came from host, which is hosting 10.00001. Okay. So then we populate the endpoint maps with 10.0.0.2 on host C, and now we have direct connection for the, so on the host C, we say on the when the packet on the way back, he populates that table saying that host 10.0.0.1 is on host A. Okay. It populates the endpoint map with 10.0.0.1 to the host C, and now we have a direct connection for the first packet in the flow between the two containers. And then from then on, all the remaining packets, they go direct, basically, see, from host A to the host B without going through, going via a bouncer. So we gotten rid of the extra hop in the middle, basically. So what we have done so far is that we have provisioned an endpoint in a very constant time across the number of RPCs, two RPCs, as I mentioned. And all the packet processing is actually fast path. Fast path means directly, because the hosts are directly talking to each other after the initial ARP call and the ARP responder call. And the fact that Mizar doesn't really take any packet and send it out to OpenFlow controller, or everything is happening at the device driver for the NIC. Okay, and the containers in turn kind of they receive the packet directly from very first packet itself all the time, basically from then on. You see. And there's no need for per flow monitoring, just like Andromeda folks do that, you know. So it's all direct path all the time, basically. So this is great. So this is basically a very base level functionality we build, which you can typically build that using OVS as well, but obviously it's much more optimal and much more efficient. But we went ahead, actually we went further. We actually extended this to add a lot more functionality to it. Okay, so because if you think so far, what we actually done is we have replaced the functionality of Open vSwitch, Linux Bridge, and IP tables with a simple 4K XTP program, basically. Okay, so now, so we thought, okay, so let's actually modify the architecture of the XTP program, the main XTP program a little bit. Okay, so we have, instead of having one single XTP program, we have many of them. Okay, and we attach one of the XTP program to the NIC and call it a primary XTP. Okay, and then when we attach multiple other XTP programs, and then based on certain matching condition in the primary XTP program, like for example, matching an IP address for an endpoint, we tail call an XTP program. So by doing that, you can see that you can build a chain, actually, it's a chain of functions. So the rest of the session is going to be covered by Phu Tran. And with that, I'm going to hand it over to Phu. Take it over, Phu. Thanks.
Thanks, Deepak. Hi, everyone. This is Phu Tran, and I'm a developer on the Mizar project. Today, I will be going over the management plane, some numbers, and a quick demo for Mizar. The Mizar management plane is built with Kubernetes. Using CRDs, we are able to extend the Kubernetes API with our own custom objects. Some of these objects are generic to any networking solution, while others are specific to Mizar. Using the Kubernetes operator framework, we are able to extend Kubernetes with domain-specific controllers for our CRDs. Three fundamental components make up the Mizar management plane. These are CRDs, workflows, and operators. Our objects are defined through the Kubernetes CRD API under the Mizar.com resource group. The operators then expose interfaces for us to act on these custom objects. Finally, the lifecycle of these objects are then handled by workflows. Each of these workflows are triggered by state changes in the respective objects. For example, The droplet object, which represents a physical interface on a node, will trigger the management plane delete workflow if its corresponding physical interface were to be removed. The Mizar management plane defines 6 CRDs. These are VPC, divider, network, bouncer, endpoint, and droplet. The VPC object details information about the VPC such as its CIDR range, its ID, and its list of dividers. The divider object has information about the divider's parent VPC and its host information such as the IP and MAC of the host. The network object has information about the network's VPC, its own CIDR range, and its list of bouncers. The bouncer object details information about the bouncer's parent network and its host IP and MAC. The endpoint object has information about the endpoint's type, its parent network, and the endpoint's IP and MAC. Finally, the droplet object has information about its current host interface's IP and MAC. In addition to our custom objects, we also handle the built-in default Kubernetes objects. Currently, we handle Kubernetes pods, nodes, and services. Pods and services directly relate to Mizar's simple and scaled endpoints respectively. Nodes and their corresponding interfaces correspond to Mizar droplets. For example, if a pod or service is created, the Mizar management plane will trigger a workflow to create endpoints. Similarly, if a node is added to the cluster, a droplet object will be created for each interface on that node. Now, we will go over some preliminary performance numbers for Mizar. In our setup, we saw that Mizar achieves near line rate packets per second at around 600K PPS. With direct path, Mizar minimizes the round-trip time and is faster than OVS. Even with the first packet going through an extra hop at the bouncer, the PPS processed by the endpoints remains close to line rate. Mizar has minimal memory overhead, both during at idle and during performance tests. With 100 endpoints per host, the memory overhead on the bouncers remains at baseline level. However, the endpoint host's memory utilization increases as more endpoints are provisioned. This is an improvement that we can do by having all endpoints on the host share the same transit agent. Compared to OVS, Mizar has significantly less CPU overhead on both the bouncer and endpoint hosts. Currently, TCP performance on Mizar caps out at around 4 gigabits per second. This can be improved by running the XDP programs in driver mode, which requires NIC support. Furthermore, XDP currently does not support hardware checksumming and TSO. However, there is ongoing work to support this. All right, let's roll the demo. For this demo, we will use Docker containers to simulate physical hosts. In this first part, we demonstrate intra and inter-network connectivity, network isolation, and the effects of removing and adding bouncers and dividers. Here, we are sending updates to the daemon running on each host via RPC to provision VPCs, networks, dividers, bouncers, and endpoints. In this next part, we show the effects of adding an additional bouncer to reduce network congestion. Here, we demonstrate how Mizar direct path works within the same network. Next, we demonstrate Mizar direct path across subnets. Finally, this part demonstrates Mizar on Kubernetes, and the scaled endpoint being used as a replacement for the traditional implementation of Kubernetes services. So that's it for today's presentation on Mizar. Thank you everyone for tuning in. Please visit github.com/mizar futureway-cloud/Mizar to learn more and try it out for yourself. Also, please look forward to the next presentation about Arctos and its usage of Mizar as a networking provider.